So with that being said, let's look at a few of these groups and look at this common behavior that we can explain now. So first of all, we pointed out the noble gases, right? These are sort of the anchor, right? Because calculations and models and these things have shown that electrons that have a full S or a full S&P, so we either have 2 for helium or 8 for the rest of the noble gases that have this S2P6 configuration, is particularly stable. It's particularly low in energy and therefore very stable. So as a consequence, we see these as showing very little reactivity, right? They're very stable, relatively inert, non-reactive, as shown in the quantum mechanical model. But that also means elements that have electron configurations that are close to this, like group 7 in the halogens, or group 1 and 2 in the alkaline metals and alkaline both metals, tend to have reasonable reactivity to try to gain or lose electrons, to have an electron configuration that matches, right? So they're trying to attain noble gas electron configurations by either losing or gaining small numbers of electrons, 1, 2, 3 electrons, to get to this matching, right? This, quote, stable configuration. So if we look back at the ions that these groups form, that's what they're doing, right? They're trying to match the electron configuration of the nearest noble gas. So if we look at the alkaline metals and the halogens, right, these are the two most reactive groups on the periodic table. The alkali metals being the most reactive metals, since they are only 1 electron away from the noble gases, right, they simply will lose that 1 electron to drop back to the nearest noble gas. So sodium will lose 1 electron to drop down to 10 electrons to be like neon, or potassium will lose that 1 electron to drop down to 18 electrons to be like argon. Right? So as a result, these alkali metals will always form positive 1 cations or positive 1 anions when they react. Halogens, right, when they form ions, right, notice they're only 1 electron shy of being like a noble gas. So what we see is when halogens form ions, they will add 1 electron or gain 1 electron to get to be like noble gas. So chlorine will gain 1, go from 17 to 18 to be like argon. Bromine will gain 1 to go to 36 electrons to be like krypton, etc., right? And so we see these always will form a -1 ion to try to have that noble gas configuration. And we can see this pattern extending out a little bit to, say, even the alkali earth metals, which are 2 away, and so they will tend to lose those 2 electrons, and you will see them forming 2+ ions, again, to get that noble gas configurations. And we see this in some group 6 elements, like oxygen, that like to form 2- ions, etc. So if we look at those common ions that we talked about, and we look at this now, we can explain why we see those, +1, +2, -1, -2, why they form those particular ions. Okay, now that we've seen how the quantum mechanical model, when looked at through this idea of electron configurations, can help us see the periodic patterns that are laid out in the periodic table and why these periodic patterns exist. And we tied them to these different properties, right? So we said that it explains why the elements in a particular group have similar properties and how we can see these sort of patterns. Now, one of the other things that get pulled out of here are not just particular properties, but trends in certain properties. So if we overlay the periodic table with particular properties, we can see how they change as we move, say, across the periodic table or up and down on the periodic table. And so throughout the book, we're going to look at some of these. We're going to look at 2 right now. And the first one is a periodic trend for the size of the atom, right? What we call atomic size. So the atomic size of an atom is determined by the distance between those valence electrons, right, the outermost valence electrons, and the nucleus. So what do we see in terms of the trends? Well, the first one we see is as we go left to right, so across a period, the atomic size gets smaller. So atoms actually get smaller as you move from left to right on the periodic table. Now, why might that be? Well, let's look at what's happening. So every step across, we add an electron, but of course, we're also adding a proton, right? The atomic number is going up 1 every time we go from one element to the next across a period. So we're putting more protons into the nucleus. So what is this doing? You put more protons, you have a greater positive charge in the nucleus. Now, this greater positive charge in the nucleus is going to apply a stronger attraction to the electrons, a greater pull on the electrons, pulling them closer to the nucleus, decreasing the size of the atom, right? So by having a greater positive charge, we're going to pull the electrons closer and resulting in a smaller atom, right? A smaller distance between those valence electrons and the nucleus. So that's how we can explain why atoms get smaller as you go across. Now, there's also a size trend as we go up and down the periodic table. So as we look at a column, atomic size gets bigger as we go down a column. So as we, go from, say, in the halogens, fluorine to chlorine to bromine, atoms get bigger. Now, why is that? Well, remember that as we move down, we go from the first period to the second period to the third period, right? We're putting electrons into the same type of orbital, but that orbital has a larger principal quantum number, right? Which means the orbitals are getting bigger, right? So if our last electron is going into, say, a 3p orbital instead of a 2p orbital, well, the 3p orbital is bigger, and so those electrons will have a higher probability of being further away from the nucleus or larger, right? Or making the distance between those valence electrons and the nucleus larger. And so as the size of the orbital increases, with increasing principal quantum number, the electrons occupy these outermost orbitals, are further away from the nucleus, giving a larger atomic radii. Okay. So we can explain the trend, again, using these sort of basic ideas. So if we look at this, we can see these trends clearly. Right? We can see as we go across, atoms get smaller. As we go down, they get bigger. And if you want to look even more globally, we can see that the biggest elements here are in the lower left-hand side of the periodic table. The smallest elements are up here in the upper right part of the periodic table. So, atomic size. The second trend, and the last topic that I want to talk about here in Chapter 9, is the trend in what's called ionization energy. So ionization energy is the energy required to remove an electron from an atom. Right? So, for example, when sodium loses that one electron to form a positive one ion, to become like neon, how much energy does it take to pull that electron away? Right? That's what the ionization energy is. So the energy required to remove an electron from an atom. So it takes more energy, right, or the ionization, it gets bigger as you move to the right. So ionization energy gets bigger as we move to the right. So if we take, say, the third period, right, chlorine has a larger ionization energy than sodium. Right? So it's going to take more energy to pull that electron away from chlorine than it would from sodium. As you go up and down, the ionization energy gets smaller. It becomes easier. Right? So if we're looking up and down, right, sodium is going to have a lower ionization energy than, say, potassium, right? It's going to be harder to pull that electron away. Sorry, I wrote that backwards. So sodium is going to be higher, than potassium. It's going to take more energy to pull that electron away from sodium than it would be for potassium. So it becomes easier to pull the electron away as you move down. Now, the easiest way to think about this trend is to think about how it relates to size. So this trend is closely related to size, and what we can say is that the smaller the atom, the larger the ionization energies. And that's simply because if you have a small atom, the electrons are held more tightly to the nucleus. It's harder to pull them away. It's going to take more energy. So as we look at these trends, follow size. So since we know the size gets smaller as you go across, the ionization energy gets bigger. So chlorine is smaller than sodium, so it's going to have a bigger ionization energy. As we go down, atoms get bigger, so ionization energy gets smaller, right? So the highest ionization energy is going to be in the smaller atoms, which are going to be at the top. And so as atoms gets bigger, it becomes easier to pull it away. And so we see smaller ionization energies at the bottom, right? So, but the big deal is the smaller the atom, the larger the ionization energy. Or if you want to look at the other way, the larger the atom, the smaller the ionization energy. All right, so this brings to a close what I want to talk about in Chapter 9. This also brings to we'll be moving next into Chapter 10, and you can look for those videos as we get into that material.